and today I want to talk to you about motion graphs. You've been dealing with motion graphs quite a bit the last few days in your physics class, and so specifically motion graphs for objects traveling at constant speed. Now, up until now, we've just kind of been looking at computer screens whenever we're talking about these motion graphs, but today I want to actually show you the motion graph that's created by this little cart traveling at constant speed down the track here. And I'm actually going to use some technology. I'm going to make some measurements. Well, I'm not going to make the measurements. I'm going to let the technology do that. And we will plot those motion graphs in real time for a real object. Before we do that, though, I do want to recap what we should expect these motion graphs to look like for an object traveling at constant velocity or constant speed. The position versus time or distance versus time, you can kind of use those synonymously, position or distance versus time. Distance versus time graph for an object traveling at constant speed is a linear graph. And so I should expect something that looks kind of like this. And then for a velocity versus time graph, it's a little different. It's still gonna be linear, but it's not gonna have a slope. It's gonna have zero slope. You guys learned that more recently than the distance versus time graphs. And we also learned that the slope on a distance versus time graph tells you the velocity, right? So if we calculate the slope of this line, we know how fast that object was going. The slope on a velocity versus time graph actually tells you something else that we're not going to talk about quite yet. But to get the velocity versus time, to get the velocity from a velocity versus time graph, all I need to do is look at that vertical axis intercept, or that y-intercept as you know it. So if let's say that the intercept was here at 10, and we're measuring our velocity in meters per second, well, that means that our object would be traveling at 10 meters per second. And if there's no slope, then that means it continues to travel at 10 meters per second for that entire time. All right, so that's just a little recap of things you should already know. So let me show you how we're actually going to plot this real world data. Now what I'm going to use is a program called Logger Pro. This is a program that years and years ago, before the pandemic, we used to use to do actual labs in our physics classes. We probably won't be doing those this year just because you get a little handsy with the lab equipment. We can't really be sharing at this point. So most of our labs probably will be virtual, but I'll do as many of these demonstrations as I can just so you see that it actually does work in the real world. So this program is called Logger Pro. You know, high schools all across the world use Logger Pro when they do their physics labs, as do a lot of universities as well. This is a pretty robust program. So our graph is going to be compiled here. The data will actually be compiled here in this table. There's going to be a lot of data, as you'll see. I'm not going to take the data, though. This guy is going to take the data. This is a motion detector. And here, let me trigger it for you. You can actually hear the sound that it makes. Those little clicking noises. Those little clicking noises, that's how it actually makes the measurements. It uses sonar, like a bat or like a submarine. It sends out sound waves. That's what the clicking noises are. And then those sound waves echo off of what they hit and come back. And then the device itself, in conjunction with the program, determines based on how long it takes for that echo to come back, it determines how far away the object is at that moment. And so on a position versus time, it just plots those changing positions. That's why you get a slope. And then for the velocity versus time, it uses those positions to calculate velocities. So again, those little noises you hear, those little clicking noises, that means that it is sending out sonar waves. And just so you can see, put my hand here, it's measuring the distance to my hand. I get farther away. Oop. Let's do that one more time. Measures the distance to my hand. I get farther away or closer, and it kind of jumps around there a little bit. It'll work much better with the actual demonstration, I promise. As long as I point it at the car. All right, so we're going to do these one at a time. I'm going to make the position versus time graph and then the velocity versus time graph. So again, for the first one, position versus time, we should expect that it's going to be linear, and it should slope up and to the right. So let's see if that's in fact what we get. So let it get warmed up a little bit so we know it's going to travel at a constant speed. And Let's try that one more time. There we go. All right, so it might not look all that pretty now, but I'm gonna go ahead and zoom in a little bit. Let's auto scale a little bit. Ah, there we go. So a little spike here. That just means that it probably lost the car a little bit. Probably lost the car, and you couldn't really it couldn't really detect exactly where the car was at. That happens. But here, it's obviously very, very, very linear on that interval right there. Now, what's nice, when you have to calculate slopes of graphs by hand, you have to pick 2 points on the line and do your rise over run. What's nice about Logger Pro is all I need to do is highlight the section that I know is linear. I don't want to highlight that section. This is bad data. You don't want to use bad data to make your models, to do your calculations, to do your analysis. What you want to do is just choose this good data that I know is representative of when the cart was moving, my hand wasn't in the way, and it was taking good measurements. And then I can actually determine the slope. Now, you won't be able to see this, but this little box right here tells you what the slope of that line is. And the slope of that line, again, the slope, in your math class, you call that M. In this class, that slope for this particular type of graph represents the velocity. And so that velocity, and this is from a position versus time graph or distance versus time graph. That velocity here is about, again, you can't see this because it's too far away. It's about 0.383. Meaning that this guy will go a little over a meter in about 3 seconds. Not very fast. But there we go. That's how fast that guy was going. Didn't have to use a radar gun or anything. All we had to do was apply the slope to the position versus time graph. Let's see what the velocity time graph would look like. So the velocity versus time graph is right here. Now, the horizontal axis is here, and it looks like the line, the velocity time graph, is right there as well. So what I'm going to do is zoom in a little bit. And again, that data, that bad data, is reflected on this little guy right here too. So that's kind of interesting. So I'm going to go ahead and zoom in here. Ooh, let's zoom in a little more. There we go. Now we're getting somewhere. There we go. So here is the horizontal axis, the time axis, or the x-axis in your math class. And here we got what amounts to a pretty horizontal line. Note that it's not exactly horizontal. There's little bumps and stuff. There's little bumps here and there. And that's just because physics is a little messier than most people think. A lot of people think that scientists are 100% correct all the time. That's definitely not the case. In science, there's no such thing as 100% certainty. There's no such thing as 100% accurate measurement. And so the measurements here weren't perfect. They're good, but they're not perfect. And any scientist that says they're 100% sure about something means they're not the best scientists. So just remember that. Science does get a little messy. Measurements get a little messy. The thing is, you just want to make your measurements as good as possible. Now here, the slope isn't going to help us. What's the slope here? The slope is 0, right? The slope of a horizontal line is 0. That does actually tell us something about the acceleration of the object, but we'll get to that soon. But the slope here is 0, but what we can do is just average all of the values, average all of the velocity values for this the entire motion to get a value for a good value for the velocity, the constant velocity of the cart. And what we do to do that is just highlight the data and click on a button that stands for statistical analysis, which is a fancy way of saying find the mean, median, and mode, and then do something called a standard deviation, which you don't have to worry about until you take statistics. But yeah, so on the velocity versus time graph, let's see what we get here. And I'm just looking for the average. I'm just looking for the average value for the velocity here. And that turns out to be 0.385. So here I get a velocity of 0.385 meters per second. Notice that both of these graphs were for the same motion, Yet I got ever so slightly different values for the velocity. Again, that's indicative of the fact that science is a little bit messy. If you ever expect to get a certain value to the 10,000th and you actually get exactly that value in a high school physics lab, you're probably cheated. You're probably going to have a little bit of error there. Now you want to minimize your error, but you don't want to cheat. So you expect actually to get values that are slightly different based on slightly different ways of analyzing the same data. Okay, so there we go. Let me just kind of zoom out here and show both of the graphs, both the velocity time graph and the position versus time graph for the same object undergoing the same motion. That's what these are. Two different ways of graphically depicting the same exact motion. For a position versus time graph, we have a non-zero slope, but it's linear. On a velocity versus time graph, yes, it's technically linear, but it's zero slope, it's a horizontal line. And again, that is what we predicted would happen based on what we've already learned from our Gizmos labs. And that's about it. Have a good day.